So for this video, we've got two more big tests that'll actually give us absolute convergence. This is section 11.6, which is absolute convergence and the ratio and root tests. Now the ratio and root tests are actually pretty valuable because they won't just tell you whether or not something is convergent or divergent, but they will tell you if something is absolutely convergent. And I made a mention of this at the end of one of the other videos. So a series is absolutely convergent if the series of the absolute values, so if I tack on an absolute value bar to everything inside of the sum, is a convergent series. Now, I believe the example I had was something like n equals 1 to infinity of cosine of n divided by n squared. This is not a proper alternating series because I can't replace anything with a negative 1 to the n, and depending on how my n's are spaced, I might have two positives in a row or two negatives. I couldn't really do the integral test on this one because it's not a positive series. It's not really decreasing, and I also wouldn't know what to do with that integral if I had to deal with it. And it's certainly not geometric or telescoping. But what I can do is compare it if I take its absolute value. This is a positive term sequence, and since cosine is between negative 1 and 1, the absolute value of cosine will be less than 1, but still greater than 0. And this is a convergent p-series. So what we say is that this series is absolutely convergent because the absolute value of the series converges. So this means, let's see, by comparison, n equals 1 to infinity of cosine of n over n squared converges. Therefore, sum n equals 1 to infinity of regular cosine of n over n squared is absolutely convergent. Which is just a little bit better than regular convergent. And in case I wasn't clear about it, this does mean that the original series, it does converge, but it converges even better. Now, on the off chance that this doesn't happen, if the series converges, regular series, but the absolute value, or the series of absolute values, does not converge, then we say that the series is conditionally convergent. And a classic example of these are maybe the sum of a sub n is an alternating series. Its absolute value terms may not necessarily converge, but by virtue of it being an alternating series, it may converge anyway. And a classic example of this here is alternating harmonic versus the regular harmonic. The regular harmonic series is the absolute value of the alternating harmonic series, but the alternating harmonic converges by the alternating series test, and the harmonic series diverges by the integral test. So the book listed it as a theorem, but I just made it a note that if the series is absolutely convergent, then of course it must be regularly convergent, because the absolute value of the series is actually going to be a larger value than the original. So we actually have two tests that will give us absolute convergence. Well, not give us, but it will determine absolute convergence for us. Basically, if the result of this test is yes, then it's absolutely convergent. If the result of the test is no, then it's divergent. And if the result of the test is confused, then we are equally confused. So the first step is the ratio test. And both of these tests are a method of comparing my series to a geometric series. It's not quite the same kind of comparison as we had for the limit comparison section, but it is essentially what we're doing. So for the ratio test, we have three possible outcomes, and it's so-called, let me before I get to the outcomes, let me list out what the test actually is. We consider the limit as n goes to infinity of the ratio of the terms of the sequence. So I do the next one divided by the previous one inside of an absolute value. And this absolute value right here is actually where we get the absolute convergence from. So I'm going to say this is equal to L. This is my limit L. Whoops. So 1, if L is less than 1, it must be a positive number because I'm taking the limit of an absolute value. But if L is less than 1, then the series of a sub n is absolutely convergent. Let me just say CVGT. If L is greater than 1, then the series is divergent. And this is where we see that we're comparing to a geometric series, because the ratio of the terms of a geometric series, right there, should fit the common ratio of the geometric series, or the geometric sequence, I could say. So this is saying as n goes to infinity, my series should look approximately geometric, or the sequence of my terms should look approximately geometric. So if eventually the ratio between the terms is smaller than 1, that's like having a common ratio of r less than 1, which means I would have convergent. My actual sum will be pretty far off from the formula we have for geometric series, but we can at least draw this conclusion. And likewise, if the ratio is greater than 1, that means my series is growing disproportionately. But we have a third case. If I'm greater than 1 or less than 1, I can also be equal to 1. If L is equal to 1, then the sum of a sub n, well, we actually don't learn anything from this. So an easy example of cases where I fit the third option, where L is equal to 1, is anytime I have a ratio of polynomials, if my series looks like a rational function, or even better, if my series is a p-series, the ratio test will always fail. It will always be inconclusive. And you can test this. You take any p-series or any series where the terms are a rational function of polynomials, you're going to get 1 every single time. And the reason it's inconclusive is because the ratio test can't tell the difference between an alternating series or a positive series. So, best example, if I try to do the ratio test on the alternating harmonic series, I'm going to get a limit of 1, and it's going to be inconclusive, even though the alternating harmonic series converges. And it would give you the same result if I tried it on the regular harmonic series. There are other poorly behaved series besides the ones I've listed, but we'll just hope we don't encounter them. So the ratio test is really good for things that have exclamation points, actually. Suppose I had the series 2n to the n divided by 2n factorial. We'll go from n equals 1 to infinity. And we'll just say I want to test for convergence. Well, I have an exclamation point here, and anytime you see an exclamation point in a series, that should be a very big indicator to use a ratio test. It's not the only time, but it's a very, very good time. So I'm going to use the ratio test, and I'm going to look at, let's see, I need the n plus 1 term divided by the n term. So I want the limit, as n goes to infinity, absolute value. I'll have 2 n plus 1 raised to the power of n plus 1 divided by 2 n plus 1, and that's factorial, divided by the original term, 2n parentheses the n over 2n factorial. This looks lovely. But let's simplify our fraction. Let's see, I'll have 2, I can do this, 2n plus 2 raised to the power of n plus 1 divided by 2n plus 2 factorial multiplied by the reciprocal, so I have 2n factorial divided by 2n to the n. And I want to try to cancel things. So what I'll do is I'll try to write out the factorials a little bit. See, I'll have 2n plus 2 to the n plus 1 divided by 2n to the n, and I'll match the factorials together. So this is 2n times 2n minus 1 times 2n minus 2 times 2n minus 3 dot 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 all the way down until 1. Let me write that. It's 3 times 2 times 1. And on the bottom, I have 2n plus 2 factorial, which means I start with 2n plus 2, then I'll have 2n plus 1, then 2n, then 2n minus 1, whoops, minus 1, dot dot dot, down until I get to 3 times 2 times 1. But what I see is that I can cancel a bunch of this stuff. I can cancel that one, and these. And in fact, I'm going to be able to cancel all the way down until I get to 1. So I have this junk down here left on the bottom. Now we can turn our attention to these n to the n like things. And in fact, I could technically factor out a 2 out of each of those, so I kind of regret multiplying that out. But this is 2 times n plus 1, all raised to the n plus 1 power. So using properties of exponents, I could rewrite this as 2 to the n plus 1 times n plus 1 to the n plus 1. Here the exponent could be kind of factored off, or I've distributed amongst the factors of the base. And on the bottom, I'll have 2 to the n times n to the n. And this is all multiplied by 1 over, I have a 2n plus 2, and I have a 2n plus 1 left over here. In fact, why don't I take this left fraction, right fraction, and factor it. So instead of 2n plus 2, I'm going to write 2 times n plus 1. Then what I'm going to be able to do is I can cancel the n plus 1 with one of these up here. So I'm just left with n plus 1 to the n. And this 2n times 2 on the bottom matches up with the 2 to the n plus 1 on the top. So I can cancel these. So my result, limit as n goes to infinity, after I cancel off all this stuff, I have n plus 1 to the n divided by n to the n. This is multiplied by 1 over 2 times n plus 1. So now the question is, what do I do? Actually, you know what? I don't need these absolute value bars anymore because everything here is positive. But what do I do with these n plus 1 to the n's over here? Well, I could rewrite this as n plus 1 over n raised to the power of n. And then I could split my limit, actually, so that this limit, this one, is equal to 0. So I need to make sure that this limit on the left is actually not infinite. So this is the limit as n goes to infinity. I can rewrite this again. This looks like 1 plus 1 over n to the power of n. That looks really familiar. So you may recognize this first one from the L'Hopital section, I believe. But this right here is actually the definition of E. If you go through the process of using logarithms and L'Hopital's rule to solve this first limit, you will get E. So this is equal to E multiplied by 0, which is simply equal to 0. Which is, of course, less than 1. Which means that this series I didn't use the root test, ratio test. Spoiling things. The sum from n equals 1 to infinity of 2n to the n over 2n factorial converges. So let me summarize cases where you want to use the root test. There is a factorial anywhere in the problem. If there's a factorial anywhere in the problem, the root test just may be your only hope. But there's also something to the n. Maybe I have some expression raised to the nth power, but it doesn't quite fit a geometric series, or maybe I have something to the nth power and it's multiplied by a whole bunch of other stuff. Well, I'd either have to try to compare it with a geometric series, maybe with direct or with limit comparison, or I could jump straight ahead and try to use the ratio test. I said root again, didn't I? It's a problem with having two similar tests in one section. If I have something to the n anywhere in my problem, or if I have an expression to the n, then it's a really good idea to try to use the ratio test for this kind of a problem. But places where I don't want to use it is perhaps maybe if I have a natural log, that might look a little bit scary, but I want to avoid rational functions of polynomials. And just about anything that will limit compare to a P series. But the only way you're going to know how to spot these cases is simply by practice. Now the other test we have out of this section is the root test, which I kept saying by accident. And the root test is we consider the limit as n goes to infinity of the nth root of the absolute value of a sub n. And here we need the absolute value just so that the nth root is actually defined, because I don't want to take the root of a negative number, because I don't even know if infinity is even or odd. Maybe it's both. I'll call this equal to L again. So 1, this has exactly the same conditions as the ratio test, but we just have a different limit to approach it with. So we say if L is less than 1, then the sum of a sub n converges absolutely. If it's greater than 1, the sum of a sub n diverges. And if it's equal to 1, it is inconclusive. Now, unfortunately, just like the ratio test, things that the ratio test is inconclusive on, the root test will also be inconclusive on. The root and the ratio tests kind of go hand in hand, and they're mostly interchangeable except for a few cases. But if you have a series and you can use both the root test and the ratio test, they will both give you the same results. They'll either both give you a limit that's less than 1. It won't give you the same limit. It probably won't give you the same limit. I'm not actually sure if there's an example. But if L is greater than 1, they will both give you an L greater than 1. And if L is equal to 1, both tests will give you an L equal to 1. So the root test is likewise unhelpful for anything that limit compares to a p-series. And there's a reason for that. So this is a remark. This is a good fact to have, and you should test these by yourself with L'Hopital's rule. But the limit as n goes to infinity of the nth root of c is equal to 1 if c is a constant, c greater than 0 is a constant. The limit as n goes to infinity of the nth root of n, this is also equal to 1. It requires a little bit more steps to show. And the limit as n goes to infinity of the nth root of n to the c, where c greater than 0 is again a constant. Actually, I don't need greater than 0, but I just need c as a constant. This will also be equal to 1. And the reason for that is I can do some voodoo with the exponents and take the c basically all the way to the outside of the limit. So I end up getting a limit of 1 raised to the power of c, which is just going to be 1. So I'm going to allow you guys to take these as facts and keep those in mind, but do be sure that you don't try to cheat with these. You don't want to screw up your algebra just to try to get these guys to show up. But these facts right here are also exactly the reason why the root and the ratio tests don't work for series which are limit compared similar to a p-series. But we have the root test because sometimes the ratio test is simply inconvenient, or the algebra is a little too messy and maybe the limit's a little too hard to deal with. I got lucky kind of with the last example, but I also had to use the ratio test because there was a factorial. I cannot use the root test if there is a factorial in the problem, because there is no way to verify what the nth root of n factorial, for example, is going to look like. So a very good example of a root test, let me see here. Let me try to make this as bad as I can. Let's see. I'll have n equals 1 to infinity. Let's see. I'll have n squared times 4n cubed minus 16 divided by 17n cubed plus 6n. Whoops. Let me try it this way. Let me do 17n cubed minus 60n squared plus 7. Yes. Hey, 7. And we'll raise this to the simple power of n. This looks terrible, right? I could try to use the ratio test on this, but I can tell I'm going to have n plus 1s all in here. I'm going to have an n plus 1 inside this n squared, and n plus 1 inside this n cubed, and n plus 1 in the exponent. I can just tell from now, from experience, that the algebra for the ratio test on this guy is just going to be awful, because I'm going to have to expand a whole bunch of things. I'm going to have a whole bunch of extra terms. I'm going to have to be writing for hours. But instead, I'm going to use the root test, because I've got some extra crap out here. I've got some gross stuff in here. But most importantly, I have an n in an exponent. So I'm going to use the root test. And I'm going to have, I want the limit of that term as n goes to infinity inside of the nth root. This is the nth root of the absolute value of n squared times 4n cubed minus 16 over 17n cubed minus 60n squared plus 7. Oh boy, raised to the n inside of absolute values. But I should make a little note here, because sometimes it's helpful. We want to know what we're dealing with, that the nth root is the same thing as the 1 over n power. So I'm going to rewrite it like that, but I'm going to break apart my absolute value bars across multiplication, because that's something you can do. A little multiplication in there. So now I have n squared to the 1 over n power multiplied by this horrible fraction. Let's see, I'm going to need parentheses here. 4n cubed minus 16 all over 17n cubed minus 60n squared plus 7 to the n in absolute values, and that's raised to the 1 over n power. So this first one I can take care of really easily. This is n squared to the 1 over n. It's already in the absolute values, so it's perfectly fine. But this is essentially n squared to the 1 over n power. Or I could consider this is the nth root of n squared. And I said before as a fact that this is going to end up being equal to 1. Over here, I can move the exponents in and out of absolute value bars. So this is 4n cubed minus 16 divided by 17n cubed minus 60n squared plus 7. But that's raised to the n, and that's raised to the 1 over n. But when I have exponents upon exponents, I multiply the exponents together. So I have n times 1 over n as the exponent here, so those cancel. So I have a product of two limits as a result. I have n squared to the 1 over n, and I've told you that's going to be equal to 1, multiplied by the limit as n goes to infinity of this guy, 4n cubed minus 16 divided by 17n cubed minus 60n squared plus 7. And I could translate this into a function of x and try to use L'Hopital's on it, but this time I'm going to use methods out of 2.6. So this is 1 times the limit as n goes to infinity, the absolute value 4n cubed minus 16 times 1, actually, this writing this kind of ugly, 1 over n cubed divided by 17n cubed minus 60n squared plus 7 times 1 over n cubed, because n cubed is the biggest thing I found in the denominator. I'm expecting to get an answer of 4 over 17. So this looks like 4 minus 16 over n cubed divided by 17 minus 60 divided by n plus 7 divided by n cubed. And even though this is in absolute values, these limits will still apply. Actually, what I should have done at some point was move the limit to the inside of the absolute value. That's why this doesn't matter. Limits will move in and out of absolute values perfectly fine. But all of these go to 0, leaving me with a final answer of 1 times 4 over 17, or just simply 4 over 17. This is a number which is less than 1. So by the root test, this is something which converges. I don't want to write this series again. I'm just going to say this series converges. And just so that we have an example of something which diverges, let's try something that looks like n equals 1 to infinity of 2 to the n squared divided by n to the n. Now, unless I had said something, there's really no indication of what this is going to do, because n to the n just might be bigger than 2 to the n squared. We're not really sure. So I'm going to use a root test, because I think the ratio test might be a little bit ugly. Which means I want the limit as n goes to infinity of the nth root of the absolute value of 2 to the n squared divided by n to the n. But since all of the terms here are positive, I can ignore my absolute values for a little bit. And I'll rewrite my nth root as a fraction. So I have 2 to the n squared over n to the n, 1 over n. And by exponent properties, this exponent will distribute across multiplication and division. And exponents upon exponents is multiplication among the exponents, so this looks like 2 to the n squared divided by n is just n, divided by n. But as n goes to infinity, I actually know what this does. But just so that we're sure, I can translate this into x goes to infinity of 2 to the x over x, which is equal to, from L'Hopital's rule, the limit as x goes to infinity of 2 to the x natural log of 2 divided by 1, which is infinite. Well, infinity is a heck of a lot bigger than 1, so this diverges by the root test. Now, the type of places you would use the root test are similar to the types of places you would use the ratio test, except the root test will not help if you have a factorial. If you have a factorial, then you basically are forced to use the ratio test. You might be able to pull off one of the direct comparison tests with a factorial, but the ratio test is a fairly safe result, or resort. Now the root and the ratio tests are very important tests for future sections. We'll get into 11.7 in the next video, which is some rough guidelines about when to use which test. For example, if my root and ratio tests are inconclusive, I'll be forced to resort to one of the other tests, such as limit or direct comparisons, or some of the best tests. But after that, sections 11.8 basically to the end of the chapter is almost exclusively going to be using root and ratio tests based on the type of series that we're going to be talking about. So certainly get these two known like the back of your hand, because they're not going to be too big on this test, but they're going to be very big for the rest of the material in the class.